So in 1952, it's a magical year, because in this year you have actually 6 papers. We will talk about mostly 4 papers by Hodgkin Huxley and also by Bernard Katz, also a Nobel laureate. So you see here 3 Nobel laureates. Bernard Katz got a Nobel Prize for the synaptic aspect, not for the Hodgkin Huxley, for the action potential. But this is a very basic paper where they showed that the action potential is an all or none phenomena. This was already known before, but here they show it again with this technique of axial resistance, axial electrode into the squid giant axon. So here I show you the all or none properties of the spike. So you can see that these numbers is the magnitude of the depolarization current injected to the squid axon. This is a small current, no current, so this is the resting potential. This is a little bit stronger depolarizing current. So you get, as you know from membranes, when you inject depolarizing current, you get depolarization, and then the voltage decays again to rest. We already learned about this. A little stronger depolarization, there is a voltage perturbation, there is depolarizing voltage, but it decays back to rest. So if the depolarization current, the depolarizing current is not strong enough, you get a perturbation, the membrane potential moves in the depolarization direction, but then it decays back to rest. But if the current is strong enough, it's a suprathreshold current. There is a threshold here, voltage threshold. And if you cross this voltage threshold, for example, here, you inject brief depolarizing current, suprathreshold, you suddenly see that the voltage, instead of going down, it goes up, and boom, it generates this new phenomena, the spike, the action potential. Goes up and then goes down, as we just discussed. If you inject a stronger current, in this case here, you get an action potential that looks very similar to this one earlier. If you inject even a stronger current, you get an action potential that looks similar. So the stronger current you inject, you get the spike. The spike has the same shape. That's why we call it all or none, because below threshold, for sub-threshold injections of depolarizing current, you don't get a spike. We can call it 0, none. If you inject enough current, suprathreshold current, you get a spike. This spike, or this spike, it's the same spike. It's an all or none. This is the all, the one. This is the 0, the none. So there is a threshold, a voltage threshold of about 10 millivolts above rest. So you have to shift the membrane potential to about 10 millivolts above the rest, from minus 70 to minus 60, or from minus 60 to minus 50. You depolarize the membrane, and then you get in the axon, boom, an all or none phenomena, the spike, with a very particular shape, going up and going down, overshooting and undershooting, the spike. So this is a very interesting phenomenon that Hodgkin Huxley started to analyze. So what are the underlying currents in the membrane? This is really the big question of Hodgkin Huxley. What makes the membrane of the axon excitable? What makes the membrane of the axon enable to, after reaching a certain voltage, to generate this all or none phenomena? What are the specific properties in the axon? Why doesn't it occur most of the time in the dendrites? What is unique about the axonal membrane that enables current to flow such that you will get this blow this boost, this all or none action potential. So in order to do this, Hodgkin-Huxley developed two techniques, actually. One that is called the space clamp, and one that is called the voltage clamp. So I want now to discuss two techniques, because these techniques, it is the technique that made the whole difference. Without these techniques, Hodgkin-Huxley would not be able to really understand the spike in a most fundamental way. So what is this technique? So space clamp is very simple. The space clamp technique means that you take an axial or long axon and makes it electrically isopotential. What does it mean? It means that when you place inside the axon an axial resistance, low resistance inside the axon, all the points along the axon become isopotential. There is no voltage drop between, let's say, this point, and this point. You made the axon, although it's long, electrically, because of this resistivity that is low axially, there is no voltage drop between this point and this point and this point and this point. So all the inside of the axon becomes isopotential. Whenever there is a spike here, immediately there is a spike there, isopotential. So the whole membrane becomes isopotential. This is not the usual case. The usual case is that when the spike starts here, it propagates, so there is a big spike here and no spike there as yet. But this they got rid of by making this axial resistance. Okay, so this is called space clamp because you clamp the space. The space becomes shrinked electrically. There are no different points in space. The space, because of this axial resistivity, high conductance inside the axon, the space becomes shrinked, and this point and these points are essentially electrically the same point. So this is the space clamp. This is simple, making the axon effectively isopotential. But the more sophisticated method is the voltage clamp, VC we shall call it, the voltage clamp. The voltage clamp, I'm not going to go into the electrical aspect, but the idea is that you want to clamp the voltage, you want to set the voltage, to fix the voltage between the inside and the outside of the membrane of the axon. So you don't want the membrane of the axon to behave independently as it wants to behave and generate a spike. You want to fix the voltage, to clamp the voltage between the inside and the outside, so that you will preset, let's say that I want the voltage difference between the inside and the outside to be 20 millivolts. I can decide and set the voltage to be 20 millivolts and don't allow it anymore to move from there, or 40 millivolts, or 50 millivolts above the rest. I want to preset and decide and fix the voltage between the two sides. Why? Because I don't want the action potential to interfere. I want to see what happens to the membrane at this fixed voltage difference. So the voltage clamp technique, which is a fast feedback system, enables the experimenter to dictate the desired voltage difference between the inside and the outside of the membrane. This electronic feedback system injects current exactly to counterbalance the excitable, the voltage-dependent current that the membrane wants to generate. I will show you that this membrane generates currents that is voltage-dependent. For any given voltage change in the membrane, there is a new current generated inside or outside between the two sides of the membrane. And you want to hold this voltage, so you need to inject a counter current to counterbalance the natural current that goes through the membrane. So this is the voltage clamp system. You feel, using this feedback system, you feel what is the current that the membrane wants to start to generate in order to blow an action potential, then you inject through the system a counter current, exactly the same current, but in the reverse direction, so you fix the voltage, and the voltage does not change. This is the basis of the voltage clamp. And because now you can fix the voltage between the two sides of the membrane, you can ask the question, what is the current that flows between the two sides of the axonal membrane for this particular voltage? If you fix another voltage, let's say you move to plus 30 millivolts above rest, what is the current that flows in the membrane for this fixed voltage? So of course, this is a very artificial system because, of course, the axon does not have voltage clamp in the regular sense, and because of this, it blows this independent, completely independent spike. But you want to control the spike, so to speak. You want to control the voltage, fix the voltage, and then measure the currents that underlie the spike. Later on, they will go back to the full spike. But now we are trying to understand what did they learn from both the space clamp, which does not allow the spike to propagate, but mostly from the voltage clamp, which enables to record direct currents through the membrane because you inject exactly the same current in the opposite direction. So you can really measure what are the currents that flow through the membrane during voltage clamp. So this is what I'm going to show you next. The current that flows through the membrane for a given voltage clamp. So let's look at it.